In this video, we're going to talk about finding limits graphically and numerically. Let's start off with an example. So let's say I have this function, f of x, and it's equal to x cubed minus 1 over x minus 1, and x obviously can't be 1 because that would make our denominator 0. We can't have that. So a limit comes in when I want to evaluate this function at x equals 1, because I can get really close to it coming in from the left-hand side and from the right-hand side. So that's where we start talking about the limit of a function as it approaches a certain point. And in this video, we're going to do that in two ways. One of them is graphically, and the other is numerically. Now, graphically, when I look at this function after I've graphed it, I notice that there is a hole at x equals 1. And if that function didn't have a hole there, that point would be at 1, 3. So I can say that the limit as f of x approaches 1 is going to equal 3. So if I wanted to prove that numerically, I would make a table of values where I would put 1 in the middle, and I would approach from what we call the left-hand side, which is more negative, coming in to be more positive on the x-axis. So that means that I'll have numbers that get really close to 1, but not quite 1, and see what their values are. And I'll also do that for the right-hand side. So that's coming in on the right to the left on the x-axis, if you like to think of it that way. So that means that I'm going to start with a number really close to 1 and get gradually a little bit bigger and see what happens. So I'm looking at this chart and it looks like 2.3, 2.7, etc. gets really close to 3. And coming in the other way, I get 3.8, 3.3, etc., getting really close to 3. Those two look like at 1, it's going to equal 3. Even though there's going to be a hole there, I can say that the limit of f of x as x approaches 1 is equal to 3. So that's how we find the limit of a function graphically and numerically. Let's try another example. So let's say I am looking for the limit of this function here as x approaches 0. So the tricky thing about that is if I plug 0 in here, it's going to give me the square root of 1 minus 1, which is 0 is out my denominator. We know that that's a problem. So graphically, if I graph this thing, I notice that there's a hole at x equals 0 and y equals 2. It looks approximately that. So I'm going to guess graphically that the limit of this function as x approaches 0 equals 2. So numerically, remember we make a chart of values that gets progressively closer to 0 from both sides, left and right. It looks like those output values get really close to 2 as well. So that means that my limit of this function is going to equal 2. Let's look at another function. So let's say I have the limit of f of x as x approaches 2 if f of x is defined as this simple piecewise function. So if x does not equal 2, meaning every other input value of x, I'm going to get y equals 1. So here's that nice straight line there at y equals 1, except it has a hole at x equals 2, and that's going to be filled in by the point 2, 0 right there. So that's my piecewise function, and I'm looking for the limit of that function as x approaches 2. The way that I like to think about this type of limit is using something called a left-handed limit and a right-handed limit. And the way that we denote the left-hand limit and the right-hand limit is much like this regular limit up here, but you'll notice that there is a negative or a positive in the exponent spot to the right of the number, so 2. So if it's coming in from the left-hand side, it's got a negative because it's coming from the negatives, and if it's got a positive, it's coming from the positive side of the x. So I look at the left-hand side of the limit, where I only care about what's happening as I approach from the left to x equals 2. So that looks like to me that y is going to equal 1. And so when I look at the right-hand limit, I do the same thing, but coming in from the right, and it looks like to me that as I approach x equals 2, y is going to equal 1 as well. Now, the great thing about having your left-hand limit and your right-hand limit equaling the same thing, that means that our original limit that we were looking for is also going to equal what our left and right hand equals. So that means that the limit of f of x as x approaches 2 is going to equal 1 in our case. Now let's take another example where I'm looking for the limit of the function, the absolute value of x over x as x approaches 0. And here I have the graph of it. So I'm going to look at this graphically. Now you might notice that the left-hand limit and the right-hand limit equal different numbers. So coming in from the left, I've got -1 here because as I approach from the left, y equals -1, and if I approach from the right, y equals 1. -1 and 1 are not the same number. So when you have different right and left-hand limit behavior, that means your limit does not exist. So we write capital D and E, and that represents does not exist in limit talk. And another limit for us here. So let's take the limit of 1 over x squared as x approaches 0. So the graph of this thing tells me that coming from the left-hand side, this thing is going to keep going up, 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 up. It's unbounded, as we say in mathematics. And also from the right, it's going to be unbounded. So because I cannot locate a limit number for this, I'm going to have to say that this limit also does not exist. And so if you find yourself looking for the limit as x approaches some kind of number and you have unbounded behavior at that number, like x equals 0 here, you're going to know that that does not exist. Our last example, I promise, is one that models oscillating behavior. So let's take the limit of the function sine 1 over x as x approaches 0. So if you ever graph this, you're going to notice that this thing oscillates over and over and over and over. And I even went onto Desmos and I tried to zoom in as far as I could at x equals 0. And if you've ever seen this on Desmos before, you know that you're going to be zooming in for a long time and really not get anywhere with it. So looking at this numerically, meaning on our chart, as I plug in different values getting closer to 0 of x inputs in terms of trig function, so that's why you see pi there, I get 1, -1, 1, -1. So because this thing oscillates from 1 to -1 as an output, that will mean that I'm not going to be able to find a limit for this. So that means the limit does not exist. And before we go, just some common types of behavior that's associated with non-existence of a limit, so the D and E. So, as we've looked at, it approaches different number from the right and left side, or it increases or decreases without bound as x approaches that number. C in our terms is going to be a constant, so just a number. And then the last one is that the function oscillates between two fixed values and it doesn't really settle on one. And that's going to do it for this video. Thanks for watching.